the universe is full of worlds, but almost none of them can ever reach us. Billions of stars, countless planets, and still no confirmed signal, no message, no visitor, no proof that anyone else is out there. This is the Fermi Paradox, one of the quietest and deepest questions in science. In this video, we explore why alien life may be common, why civilizations may vanish before they're heard, and why the silence of space may never give a simple answer. If you enjoy calm space documentaries, please like this video and subscribe to the channel. The observable universe extends as the widest known region from which light has had time to reach present instruments. It is not the whole universe, and it is not an edge in space. It is a horizon formed by time, expansion, and the finite speed of light. Every direction leads outward through older light, and every distant galaxy appears as it was when its light began its long movement across space. The farther the view reaches, the farther back in cosmic history it looks. This outermost region gives the Fermi Paradox its first quiet setting, because any question about life elsewhere begins inside a universe so large that distance itself becomes a barrier before any other barrier is considered. The universe is about 13.8 billion years old, yet the observable region reaches much farther than 13.8 billion light-years in every direction, because space itself has expanded while light has travelled. The farthest visible matter is now tens of billions of light-years away. This does not mean that light has moved faster than light. It means the space between the light and the observer has stretched during the journey. A light-year is the distance light travels in 1 year, and even that single unit is already too large for ordinary experience. On the scale of the observable universe, such distances become almost still, like a measure too vast to feel motion inside it. At this outer scale, the universe appears nearly uniform in its broadest pattern. Galaxies fill space in every direction, arranged in great threads, sheets, and open voids. This pattern does not show purpose or design. It is the result of gravity slowly drawing matter into denser regions after the early universe begins in a hot, dense state. The same physical laws appear to operate everywhere that astronomers can observe. Hydrogen shines in distant gas. Gravity bends light around massive objects. Young galaxies appear different from nearby older galaxies because they are seen at earlier times. The deepest views do not show empty darkness alone. They show that the universe contains structure across almost every reachable direction. The Fermi Paradox begins with a plain tension. The universe is vast. Stars are numerous, planets appear common, and the ingredients for chemistry are widespread. Yet no confirmed evidence of extraterrestrial life or intelligence has been found. The paradox is not a formal contradiction. It is a question about expectation and evidence. If many worlds exist, and if some worlds can produce life, and if some life can become technological, then signs might be expected somewhere. The silence is not proof that nothing exists. It is a measure of how little has been detected across a region almost beyond comparison. At the scale of the observable horizon, the search for life is shaped by limits that cannot be removed by better patience alone. Light from the most distant galaxies has travelled for billions of years. Any signal from those regions would also be ancient. If a civilization existed there long ago, its present state would remain unknowable from Earth for immense periods. If a signal left today from a very distant galaxy, it would not reach Earth until far beyond any human timescale. The universe may contain events that are real and forever separated from direct contact by distance and expansion. Some regions are not merely far away. They are moving away so quickly because of cosmic expansion that signals sent now may never arrive. This horizon creates a first reason why the universe can be full of things and still seem silent. Observation is not the same as access. Astronomers can receive old light from distant matter, but they cannot inspect distant planets in detail across most of cosmic space. A galaxy may contain billions of stars, yet from far away it becomes a faint shape, a small glow, or a smudge in a deep image. Inside that glow, planets are hidden, atmospheres are hidden, oceans, rocks, clouds, and possible living systems are hidden beneath distance. The larger the scale becomes, the less individual detail remains. Vastness increases the number of possible worlds, while also reducing the chance of knowing any one of them clearly. The early universe also matters at this outer boundary. The oldest light observable today comes from a time when the universe becomes transparent after its first hot phase. Before that time, light cannot travel freely through space because matter is too dense and charged particles scatter it. This ancient glow is known as the cosmic microwave background. It is not a place with stars or planets. It is a record of a young universe before galaxies have fully formed. In that early era, life as understood by science cannot yet exist, because the heavy elements needed for rocky planets, water-rich bodies, and complex chemistry have not yet been made in stars and spread into space. This fact narrows the meaning of cosmic abundance. The universe may be large, but not every part of its history is equally suitable for life. The first stars must form, live, and die. They must create elements such as carbon, oxygen, silicon, and iron. Later stars and planets must form from these rich clouds of gas and dust. Stable environments must last long enough for chemistry to organize and evolve. From the outermost view, the question is not only how much space exists, it is also how much useful time has existed for life-bearing worlds to form and change. Space and time are both filters. The observable universe contains countless galaxies, but the ability to detect life does not grow simply with the number of galaxies. Distance dims light, expansion stretches wavelengths. Dust absorbs and scatters radiation. Instruments collect only a thin stream of information from extremely remote objects. Even when a telescope sees a distant galaxy clearly enough to study its broad properties, it cannot usually separate the light of individual Earth-sized planets. The signs most relevant to life are small compared with the brightness of stars and galaxies. A living planet may alter its atmosphere, but across cosmic distance that alteration becomes a faint mark inside a faint mark. The outer horizon also changes the meaning of communication. A radio signal, a beam of light, or any other message cannot cross the universe instantly. It must travel through space at a finite speed. Across intergalactic distances, a reply would require millions or billions of years. Communication in any ordinary sense becomes impossible. A signal may be detectable as a one-way trace, but not as a conversation. This makes the question of aliens different from the question of neighbors. At the scale of the observable universe, other life, if it exists, may belong to the same cosmos while remaining outside any shared moment of contact. The Fermi Paradox often feels sharp because the universe contains so many stars, yet at the largest scale, the silence is softened by the limits of observation. The absence of confirmed evidence does not carry the same meaning across all distances. It means that within the small portion of the universe searched with available methods, no sign has met the standard of confirmation. It does not mean that every galaxy has been examined. It does not mean that every signal has been heard. It does not mean that every kind of life would be visible. The outer universe holds more possibilities than present instruments can separate. This first region remains calm and impersonal. It is a horizon of old light, expanding space, and distant structure, it shows that the question of life elsewhere begins not with imagined visitors, but with scale. The universe is large enough to make life seem plausible in many places, and large enough to keep those places hidden. It offers abundance and separation at the same time. In that wide boundary, the silence around Earth is not yet an answer. It is the first condition of the search, a quiet produced by distance, time, and the slow arrival of light from far beyond the reach of any present journey. Beyond any single galaxy, the universe forms a vast connected pattern of matter and open space. Galaxies do not sit like scattered points in a simple empty field. They gather along long threads and broad sheets, separated by immense regions where few galaxies are found. This structure is often called the cosmic web, a term for the large-scale arrangement of matter shaped by gravity over billions of years. It is not a solid web and not a designed pattern. It is a slow result of tiny early differences in density growing under gravity, while cosmic expansion carries the whole pattern outward. At this scale, the Fermi Paradox enters a region where abundance becomes almost difficult to hold in thought, because every bright knot may contain billions or trillions of stars, and every star may belong to a history far older than human technology. The cosmic web is visible only through careful observation and mapping. A telescope image may show a patch of sky filled with galaxies, but the larger pattern requires distance measurements, redshifts, and long surveys. Redshift is the stretching of light toward longer wavelengths as space expands or as objects move away. It helps astronomers estimate how far away galaxies are and how quickly they're receding. When many redshifts are measured, galaxies appear arranged in great structures across space. These structures do not prove that life is common. They show that the environments in which stars form are widely distributed. They show that the universe offers many places where planets may arise, while also placing those places at distances so great that individual worlds disappear into collective light. In this broad region, galaxies are the main islands of ordinary matter. Each galaxy contains stars, gas, dust, stellar remnants, and invisible dark matter that reveals itself through gravity. Dark matter is matter that does not emit or absorb light in ordinary ways, yet it affects the movement of galaxies and the growth of structure. It is not known to be a material for life, and its nature remains uncertain. Its importance here is gravitational. It provides much of the mass around which ordinary matter gathers. Without the pull of dark matter in current models, galaxies would not form in the same way. The cosmic web is therefore not only a map of shining objects, it is also a map of gravity's long influence on visible matter. Galaxies vary in form and age. Some are broad spirals with disks and arms. Some are elliptical systems with older stars and little cold gas. Some are irregular, shaped by encounters and internal motion. In younger cosmic times, galaxies are often smaller, more turbulent, and more active in forming stars. Over billions of years, they merge, grow, lose gas, gain gas, and change. This means that the universe does not offer one kind of galactic environment for life. It offers many. Some galaxies contain heavy elements in large amounts. Some are poorer in heavy elements. Some are calm for long periods. Some hold energetic centers and frequent bursts of star formation. The number of galaxies is large, but the usefulness of each environment for long-lived stable planets differs. The Fermi Paradox becomes less simple in this region, because the presence of many galaxies does not automatically create many detectable civilizations. A galaxy is not only a container of stars, it is a changing system with radiation fields, supernovae, gas flows, and gravitational disturbances. Supernovae are explosions of dying stars that can spread heavy elements while also bathing nearby regions in high-energy radiation. Galaxy centers may host massive black holes that release energy when gas falls toward them. Stellar density can alter the stability of planetary systems. A world can form in a galaxy and still lack a steady surface environment for long periods. At the cosmic web scale, life is possible only through local conditions hidden inside each galaxy's larger history. Even if many galaxies contain living worlds, the gulf between galaxies makes discovery difficult. The nearest large galaxy beyond the Milky Way, Andromeda, lies millions of light-years away. Other galaxies lie far beyond that. A signal crossing such distances would arrive after millions, hundreds of millions, or billions of years. Across such times, a civilization that sends a signal may change, vanish, or become unrecognizable before the signal is noticed. A receiving species may also not exist when the signal arrives. The question of where aliens are becomes partly a question of whether two histories can overlap through space and time. The universe may contain many beginnings that never share a reachable present. Galaxies also concentrate light in ways that hide small things. From far away, a galaxy's stars blend into a combined glow. A single technological planet would be faint beside its star, and its star would be faint beside the light of its galaxy. Detecting life in another galaxy would require signals or effects strong enough to rise above natural sources. Natural objects already produce many kinds of radiation. Stars flare, gas clouds emit, black holes feed, pulsars pulse with regularity. A possible artificial signal must be separated from these natural patterns with care, and extraordinary claims require clear evidence. So far, no extragalactic signal has been confirmed as a sign of intelligence. The cosmic web also suggests why isolation may be normal rather than strange. Matter gathers into separated systems, and the spaces between systems are enormous. The web connects galaxies through gravity and history, but not through easy travel, even within dense clusters of galaxies. The distances between individual star systems remain immense. There is no known method by which matter, ships, or messages can ignore the speed of light. Concepts of intergalactic travel remain outside demonstrated technology. The observed universe allows movement, but it does not make movement easy. It offers paths of light and gravity, not roads in any ordinary sense. A further limit comes from cosmic time. Galaxies in the distant universe are seen at earlier stages, sometimes before enough heavy elements are widespread for many rocky planets like Earth. Heavy elements are made over generations of stars. The earliest galaxies may contain stars and gas, but not yet the chemical richness found later in mature systems. This does not remove all possibility of planets, but it changes expectations. Life as known depends on chemistry that must be built by stellar processes before it can be included in new planets. The cosmic web grows while the universe becomes chemically enriched. The outer pattern holds both early scarcity and later richness. At this region, the Fermi Paradox is surrounded by a quiet balance between numbers and limits. The number of galaxies is enormous. The number of stars within them is enormous. Yet every step from a galaxy to a living world requires layers of conditions that are not visible from the largest maps. A galaxy must contain the right elements: stable stars, long-lived planets, suitable climates, and enough time. A technological species must arise, produce detectable signs, and do so while another species is able to notice. Each condition may be common or rare. Science does not yet know enough to assign a firm answer. The cosmic web, therefore, does not solve the paradox. It widens it. It shows that the universe provides many settings, but it also shows that most of them are unreachable in detail. The great threads of galaxies shine across deep space, but they do not speak in any confirmed voice. They are known through light that has travelled for ages, through spectra, maps, and patient measurement. Their silence may come from absence, distance, timing, weakness of signals, or forms of life that do not alter their surroundings in ways visible across the dark. Within this broad galactic web, the search remains a study of both abundance and restraint, held between the richness of matter and the narrowness of what can be known. Around the Milky Way, beyond the bright disk and its crowded lanes of stars, there is a much thinner region known as the outer halo. It is not a sharp shell and not an empty wall. It is a broad, sparse realm where old stars, globular clusters, streams of disrupted systems, and invisible dark matter move on wide paths around the galaxy. From this region, the Milky Way is less like a flat band of light and more like a gravitational centre surrounded by faint traces of ancient history. The Fermi Paradox becomes quieter here, because the outer halo shows that a galaxy can contain many places where stars exist, while only some regions may offer the steady richness needed for planets and life as known. The outer halo is made of objects spread across great distances. Stars in this region are usually separated by far more space than stars near the Sun. Many of them are old and metal-poor. In astronomy, metals are elements heavier than hydrogen and helium. The word does not mean only iron or copper. It means the heavier elements made by earlier generations of stars. A metal-poor star forms from gas that has not yet been strongly enriched by many stellar deaths. Such stars are important records of early galactic history, but their ancient chemistry may make rocky planet formation less likely than in regions with more heavy elements. This does not make planets impossible around every old halo star. It means the raw materials for Earth-like worlds are generally less abundant. Globular clusters belong to this outer region as some of its most striking structures. A globular cluster is a dense, round collection of many old stars held together by gravity. These clusters orbit the Milky Way like ancient companions. Their stars often formed early, before the galaxy reached its present shape. The density inside a globular cluster can be high, especially near its center. Close stellar passages can disturb planetary orbits over long times. This does not rule out all planets in such clusters, and some planets have been found in old stellar environments. Still, a dense cluster may be less calm than a thin, quiet neighborhood around a single stable star. For life requiring long continuity, crowding can be a difficulty. The outer halo also contains stellar streams. These are long trails of stars pulled from smaller galaxies or clusters, as the Milky Way's gravity tears them apart. They show that the galaxy has grown by gathering smaller systems across time. Each stream is a remnant of motion and loss, a slow scattering of stars along wide orbits. Such structures matter to the Fermi Paradox because they show that galaxies are not perfectly settled homes. They assemble, disturb, and absorb. Some stars that now belong to the Milky Way may have formed elsewhere. Their planets, if any exist, carry histories shaped by earlier systems. A living world in such a setting would still depend on local stability, even while its star follows an ancient path through the larger halo. In this sparse region, the night around a planet would be different from the sky near the galactic disk. Fewer nearby stars would brighten the darkness. The central disk of the Milky Way might appear as a distant luminous structure across one side of the sky. depending on the star's orbit and position. This image is useful only as a way to understand environment. A halo world, if rocky and stable, could orbit its star under the same laws of gravity and light as any other planet. Yet the broader surroundings would be thin, old, and chemically different from regions where new stars still form from enriched gas. The setting would be quieter in some ways and poorer in materials in others. Star formation in the outer halo is limited compared with the galactic disk. Much of the halo's visible population is ancient. Gas is not gathered there in the same cold, dense clouds that form many new stars in the disk. Without frequent new star formation, there are fewer young planetary systems and fewer fresh chances for life to begin around newly formed stars. The halo is therefore not only far from the centre, it is also far from the main processes that keep building new stars and planets in the Milky Way. It preserves old motion more than it creates new systems. Radiation conditions in the halo may be gentler in one sense. There are fewer nearby massive young stars and fewer dense star-forming regions where supernovae occur frequently. A planet in a very sparse part of the halo might avoid some hazards associated with crowded stellar nurseries, but habitability does not come from low danger alone. It also requires suitable elements, stable planetary formation, long-lived climates, and protective conditions on or near the planet. Too little disturbance can be helpful, while too little chemical richness can be limiting. The halo shows that safety and fertility are not the same thing. The outer halo is also difficult to search. Its stars are faint and widely scattered. Many are far from Earth, and planets around them are harder to detect than planets around nearer disk stars. Common methods for finding exoplanets depend on careful measurements of starlight, such as tiny dips when planets pass in front of stars or small shifts caused by planetary gravity. These methods work best under favourable conditions, often with brighter or closer stars. Halo stars do not provide the easiest targets. Therefore, the absence of clear signs of life from the halo carries limited meaning. It may reflect the difficulty of observation as much as the actual presence or absence of inhabited worlds. The Fermi Paradox is sometimes framed as though every star has an equal chance to become a cradle for intelligence. The halo suggests a more layered view. Stars are not placed in identical circumstances. Their age, chemistry, orbits, neighbours, and histories differ. A very old star with few heavy elements may have fewer rocky planets. A star in a dense cluster may have planets disturbed by close encounters. A star in a stream may belong to a long history of galactic merging. None of these facts creates certainty about life, but each adds a filter between the simple count of stars and the expectation of detectable civilizations. From the outer halo inward, the Milky Way is not yet a welcoming disk of sun-like neighbourhoods. It is first a faint archive. It holds ancient stars, low-density space, and the remains of smaller systems. It records how gravity builds a galaxy slowly and unevenly. If life exists somewhere in this region, it would still be part of the same physical universe, shaped by chemistry, light, rock, and time. Yet its world would be hidden among old stars and enormous separations. The silence of the halo does not prove emptiness. It shows that some parts of a galaxy may be too sparse, too old, too poor in heavy elements, or too difficult to examine for silence to be simple evidence. In this outer region, the paradox rests in a dim and patient field of ancient motion. Inside the broad halo, the Milky Way gathers most of its visible stars into a flattened region known as the galactic disk. This disk is not a solid surface. It is a wide rotating structure made of stars, gas, dust, and magnetic fields, all moving around the galactic center under gravity. From within it, the Milky Way appears as a pale band across the sky because the solar system lies inside the disk and looks along its crowded plane. This region is richer and more active than the outer halo. It contains many of the stars that can host planets, many of the clouds that form new stars, and much of the heavy element material needed for rocky worlds. The Fermi Paradox becomes more immediate here, because this is the kind of region where the simple question begins to feel stronger. If the galaxy holds so many stars and planets in its disk, the absence of confirmed contact becomes harder to ignore, though still not easy to interpret. The disk has structure, but its structure is not fixed like a pattern carved into stone. Stars orbit the galactic center at different distances, and gas clouds move, collide, cool, and sometimes collapse. Dust grains drift through interstellar space, absorbing some light and glowing faintly in longer wavelengths. Hydrogen gas spreads through the disk in both atomic and molecular forms. Molecular hydrogen gathers in colder clouds where new stars can form. These materials matter because planets are built from what remains around young stars after star formation. A disk rich in heavy elements and dust can produce rocky planets, icy bodies, and the smaller solids that grow through collisions into larger worlds. The Sun belongs to this disk, in a region neither at the crowded center nor at the far edge. Its location helps frame the search for life elsewhere. Earth does not orbit a rare star in the sense of being the only planet-bearing system known. Modern observations show that planets are common around stars in the Milky Way. Many stars have planetary systems, and many systems differ greatly from the solar system. Some planets orbit close to their stars. Some are larger than Earth but smaller than Neptune. Some stars host multiple planets packed into tight orbits. The disk therefore contains not only stars but many arrangements of worlds. This abundance is one reason the Fermi Paradox remains powerful. Still, the disk is not uniformly suitable for life as known. Toward the inner regions, stars are more crowded, radiation may be stronger, and stellar encounters become more likely over long periods. Toward the outer regions, heavy elements may be less abundant, although not absent. Between these extremes, some astronomers discuss a possible galactic habitable zone, meaning a broad range of galactic locations where conditions may be more favourable for long-lived habitable planets. This idea is useful but uncertain. It does not mark a hard ring of life and non-life. It describes a balance among chemical richness, star formation history, supernova rates, and orbital stability. The disk contains many local environments, and each may change over time. Stars in the disk differ in mass, brightness, and lifetime. Massive stars shine strongly but live briefly, sometimes only millions of years before ending in violent deaths. Small red dwarfs can live for far longer than the current age of the universe, but their planets may face strong flares, close orbits, and tidal locking, depending on conditions. Sun-like stars live long enough for complex planetary histories, yet they are only one part of the stellar population. The disk's abundance does not remove these differences, it multiplies them. For every stable star with suitable planets, there may be many stars whose environments are harsher, shorter-lived, or difficult for life as known. The galactic disk also has a history of enrichment. Heavy elements are formed in stars and stellar explosions, then return to interstellar gas. New generations of stars form from this enriched material. Over time, the disk becomes more chemically capable of building rocky planets and complex minerals. Earth itself forms from material that has passed through earlier stellar processes: calcium in rock, iron in the core, oxygen in water. and carbon in living chemistry are all part of that long cycle. Life on a rocky planet therefore depends on a galaxy having enough previous stellar history. The disk provides this history more clearly than the outer halo, because it continues to form and recycle stars. Yet recycling also brings disturbance. Supernovae can seed the disk with heavy elements, but nearby explosions can strip atmospheres, alter surface radiation, or affect climate chemistry. Star-forming regions can be energetic and chaotic. Young stars often produce strong radiation and winds. Planetary systems may be reshaped early by migration, impacts, and interactions with leftover material. A stable world may require both a rich beginning and a quieter maturity. The disk offers ingredients and hazards together. This mixture makes the Fermi Paradox more complex than a count of planets. The existence of planets is only the first stage in a chain of conditions. At this scale, the search for other civilizations must also consider the motion of stars around the disk. The Sun and nearby stars orbit the galactic center over hundreds of millions of years. Stellar neighborhoods do not remain perfectly fixed. Stars pass through different regions of the disk, though close encounters remain uncommon in the Sun's neighborhood. A civilization that develops around one star is carried along by galactic rotation. Its signals spread outward as expanding shells of light, becoming weaker with distance. Other stars move through those shells at their own times. Contact would require not only the existence of technology, but also the right timing, direction, strength, and method of detection. The disk contains dust and gas that can both create and conceal. Dust helps planets form, but it also blocks visible light. Radio waves can pass through some dusty regions more easily, while other wavelengths reveal cold gas or warm dust. Astronomers use many kinds of light to study the galaxy because no single view shows everything. The same problem applies to the search for life. A civilization might use signals that are not aimed at Earth, are too weak to detect, are brief, or are hidden among natural noise. A biosphere may change a planet's atmosphere without producing technology at all. The disk may hold many living worlds that remain invisible from afar. The Fermi Paradox in the galactic disk is therefore not a simple accusation against the universe. It is a meeting between scale and uncertainty. There are many stars, there are many planets, there are materials for rocky worlds, there are long spans of time, but the path from star to planet, from planet to life, from life to intelligence, and from intelligence to detectable signal, contains unknown steps. Some steps may be common, some may be rare. Present science cannot yet measure them with confidence. What is known is that the disk is a richer region than the halo, and this richness makes the silence more meaningful, while still leaving many possible explanations. The Milky Way's disk turns slowly in the dark, carrying stars, clouds, and worlds around its center. It is a broad plane of matter rather than an empty backdrop. It holds the chemistry of planets, the births of stars, the deaths that enrich new clouds, and the long, stable intervals in which surfaces can cool under starlight. It is the first region in the inward path where the possibility of life begins to feel less distant and more local to the galaxy that contains Earth. Yet its silence remains unbroken by confirmed evidence. The disk offers many places where life might arise, and many reasons why that life may remain unseen. In this region, the paradox becomes a quiet pressure inside abundance, not a conclusion, but a measured uncertainty spread across the rotating light of the Milky Way. Within the galactic disk, the spiral arms appear as broad, bright lanes where gas, dust, and young stars are more concentrated than in many spaces between them. They are not rigid arms rotating like solid spokes. They are patterns in the disk, shaped by gravity, motion, and waves of density moving through stars and gas. As material passes through these denser regions, gas clouds can be compressed, and some of them collapse into new stars. The arms therefore become visible through young massive stars, glowing gas, and dark dust that marks the places where matter gathers. In the inward path of the Fermi Paradox, this region is important because it shows where the galaxy builds many of the stars and planets that later may become settings for life, while also showing why birthplaces can be restless and hazardous. A spiral arm contains cold molecular clouds, warmer atomic gas, dust grains, young stars, and older stars passing through. The bright blue stars that make arms stand out are massive and short-lived. They shine strongly, produce intense ultraviolet radiation, and end their lives after much shorter times than smaller stars. Their presence reveals recent star formation. It does not mean that all stars in an arm are young, but it makes youth more visible there. The same regions that form many stars also form disks of leftover material around young stars. Inside those disks, dust and ice can gather into larger bodies, then into planets and smaller objects. In this way, the arms are places where planetary systems begin in large numbers. The raw materials in spiral arms are not quiet. A cold cloud may look still from far away, but inside it there is turbulence, gravity, magnetic pressure, and radiation from nearby stars. Some parts collapse, other parts are pushed apart. Young stars release winds and jets. Massive stars carve bubbles in nearby gas. When they explode as supernovae, they send shock waves through surrounding clouds and scatter newly formed heavy elements. These processes can both support and threaten the conditions needed for life. They help enrich future planetary systems with elements, but they can also expose young worlds to strong radiation and disturbance. The same stellar death that supplies material for rocks and chemistry may make nearby environments unstable for a time. Heavy elements are central to the meaning of spiral arms: carbon, oxygen, silicon, iron, and many other elements do not appear in large amounts at the beginning of cosmic history. They form inside stars, in stellar winds, and in explosive events. Spiral arms gather gas that has been enriched by earlier generations. When new stars form from such gas, their planets may contain rock, metal, water ice, and complex chemistry. This enrichment is one reason the Milky Way can host Earth-like materials at all. The arms act as regions of renewal, where old stellar products become part of new systems. Life as known depends on this long circulation of matter through stars and clouds. Yet the earlier stages of a planetary system can be violent. Dust grains collide and stick. Larger bodies strike one another. Giant planets may move inward or outward while interacting with gas disks. Smaller worlds can be scattered. Comets and asteroids may deliver water and organic material, but impacts can also reshape surfaces. In spiral arms, where star formation is active, neighbouring massive stars may remove gas from young disks or bathe them in radiation. A young planet's future may depend on its distance from its star, the mass of its atmosphere, the stability of its orbit, and the timing of nearby energetic events. The arms create possibilities, but they do not guarantee gentle beginnings. For the Fermi Paradox, spiral arms complicate the idea that more star formation always means more life. A region that forms many stars may also produce many short-lived massive stars, frequent supernovae, and strong radiation fields. A region between arms may form fewer new systems but may be calmer for mature stars and planets. The best conditions for long-lived surface life may involve a sequence birth in enriched material, later survival in a quieter environment, and enough time for climate and chemistry to persist. The spiral pattern becomes part of a planet's wider history, because a star can move through arm regions and interarm spaces during its orbit around the galaxy. The Sun does not remain fixed relative to every spiral feature across deep time. Like other disk stars, it travels around the galactic center. Its path may pass through denser and less dense regions over long intervals, though the exact history of such passages is difficult to reconstruct. If a planetary system crosses a spiral arm, it may experience a region with more gas clouds and more young massive stars than in quieter parts of the disk. Whether such passages have strong effects on planetary habitability remains uncertain. Observations indicate that galactic environment can matter, but the details for any single world require careful evidence. The important point is that life, if it appears, develops inside changing surroundings rather than in a perfectly isolated setting. Spiral arms are also visually misleading in one way. They seem crowded on galactic maps, but the distances between individual stars remain enormous. Even in a bright arm, stars are usually separated by light years. A civilization in one system would not see neighboring systems as close in any practical sense. Travel between stars would remain difficult, requiring energy, time, and protection from deep space conditions. Signals would still weaken as they spread. The arm may contain many possible worlds, but each world remains held around its own star, separated from the next by dark distance. Abundance in a map does not become closeness in experience. Searches for life within such regions face several limits. Dust in spiral arms can block visible light. Young stars can be active and noisy across many wavelengths. Natural radio emission, infrared glow from dust, and energetic events can crowd the background. Detecting a small planet's atmosphere or a weak artificial signal against such complexity requires precise instruments and long observation. Some signs may be easier around calmer, nearer stars than in distant bright star-forming regions. Therefore, the most active parts of the galaxy may not be the easiest places to examine for life, even though they are rich in new systems. The spiral arms show the galaxy as a place of making rather than only a place of waiting. They gather the materials of future planets, shine with young stars, and carry the products of stellar death into new clouds. They hold the first broad settings in which the ingredients of life become common, but they also contain forces that may interrupt fragile beginnings. Their role in the Fermi Paradox is neither simple support nor simple obstacle. They increase the number of worlds and increase the range of hazards. They make life more plausible in the long history of the Milky Way, while also reminding science that habitability depends on calm intervals after energetic origins. In this region, the question of alien life becomes a question of survival through formation. A planet may begin with the right materials and still lose its atmosphere. It may gather water and later freeze, dry, or become unstable. It may orbit a star born in a cluster and later drift into quieter space. It may remain sterile, become microbial, or develop along paths not yet known from evidence. The spiral arms do not answer these possibilities. They provide the moving lanes in which many of them begin. Their brightness is not a signal from intelligence, but the glow of natural processes making stars and worlds. Within those lanes, the silence continues, surrounded by creation, disturbance, and the slow sorting of matter into places where life may or may not endure. Nearer to the Sun, the Milky Way becomes less like a grand pattern and more like a neighborhood of individual stars. This local stellar neighborhood is a small region by galactic standards, yet it remains enormous by human measures. It contains red dwarfs, orange dwarfs, yellow stars, white dwarfs, brown dwarfs, and many faint objects that are difficult to see without careful instruments. Some stars move alone. Some belong to pairs or larger systems. Each has its own age, brightness, chemical composition, magnetic behavior, and history of planet formation. In this region, the Fermi Paradox becomes more concrete, because the search is no longer aimed at distant galaxies or broad spiral arms. It turns toward nearby stars, the places most accessible to telescopes and the first places where evidence would be expected if life were common and easily detected. The nearest known stellar system to the Sun is Alpha Centauri, a triple system that includes 2 Sun-like stars and a small red dwarf. Even this nearest neighbour is more than 4 light-years away. A light-year is already a vast distance, and 4 of them remain far beyond present crude travel. Signals can cross that gap in a few years, but spacecraft moving at current practical speeds would require far longer. The closeness of nearby stars is therefore relative. They are close enough for detailed astronomical study compared with the rest of the galaxy, yet distant enough that direct exploration remains extremely difficult. This is one reason the silence of nearby space carries weight without becoming final proof. Most stars in the local neighborhood are red dwarfs. A red dwarf is a small, cool, long-lived star. These stars are faint, but they are numerous because they shine weakly. Their temperate planets must orbit close in order to receive enough energy for liquid water on the surface. If other conditions allow, close orbits create special problems. A planet may become tidally locked, meaning one side tends to face the star while the other faces away. Strong magnetic activity and flares may affect atmospheres, especially when a planet is near the star. These challenges do not make life impossible, and research continues to study whether atmospheres and oceans can redistribute heat. They do show that the most common kind of star may not offer conditions identical to Earth's. Sun-like stars are less common than red dwarfs, but they remain important because Earth provides one known example of life around such a star. A Sun-like star has a stable main period of hydrogen fusion lasting billions of years. During this time, planets may have long intervals for geology, climate, and chemistry to change gradually. The Sun itself becomes a reference point, not because it is proven to be unique, but because it is the only life-bearing case known. When astronomers search nearby Sun-like stars, they are searching for settings that may share some broad features with the solar system. Still, similarity in star type does not guarantee similarity in planets. Planet formation produces varied outcomes even around stars with related properties. Many nearby stars are members of binary or multiple systems. In such systems, 2 or more stars orbit a shared center of mass. Planets can exist in some binary systems, either orbiting one star while the companion lies farther away, or orbiting both stars at a wider distance. Stability depends on the separation and motion of the stars. Some binary arrangements may disrupt planet formation or long-term planetary orbits, while others may allow stable worlds for billions of years. The local neighborhood is therefore not a simple set of isolated suns. It is a mixture of gravitational arrangements, each with its own possible effects on habitability. White dwarfs also occupy the local region. A white dwarf is the dense remnant left after a star like the Sun sheds its outer layers and no longer fuses elements in its core. Such objects are not places where Earth-like life is expected to begin in the usual way, because their earlier stellar evolution can strongly alter or destroy nearby planets. Yet planets and planetary debris can exist around white dwarfs, and their polluted atmospheres can reveal the remains of rocky material. These remnants help astronomers understand that rocky bodies form widely. They show that planetary systems can survive in altered forms after a star changes, but they also show that stellar evolution can end long, stable eras. The local stellar neighborhood is where many exoplanet searches become strongest. Nearby stars are brighter and easier to measure than distant ones. Small shifts in their motion can reveal orbiting planets. Tiny dips in starlight can show planets passing in front of them. Direct imaging becomes slightly more feasible when a system is close, although separating a faint planet from a bright star remains very difficult. Nearby planets also offer better chances for studying atmospheres. If the planet passes in front of its star or if future instruments can isolate its light, the closer a world is, the more information can be gathered from the thin stream of photons that reaches Earth. Even so, the search remains incomplete. Not every nearby star has been examined with equal sensitivity. Some planets are difficult to find because their orbits do not line up with Earth's view. Some are too small, too far from their stars, or too quiet in their gravitational effects. Some systems have activity that hides or imitates planetary signals. The local neighborhood may contain worlds not yet detected, and among detected worlds, many remain poorly understood. Knowing that a planet exists is not the same as knowing whether it has air, water, geology, or life. The Fermi Paradox often begins with the known abundance of planets, but the evidence becomes thinner when it tries to move from planets to living planets. The silence nearby has special importance because nearby stars are the easiest targets for signals. Radio searches often focus on stars close enough that a transmitted signal would not be weakened beyond hope by distance alone. Optical searches may look for short pulses of light. Infrared surveys may look for unusual waste heat, although natural explanations must be considered first. So far, no confirmed technosignature has been found around nearby stars. A technosignature is a sign that could indicate technology, such as a narrow radio signal or unusual energy use. The absence of confirmed detections may mean that technological civilizations are rare nearby, that they do not transmit in detectable ways, that searches have been too limited, or that timing has not overlapped. Timing is especially important in the local neighborhood. A civilization might use strong radio signals for only a short part of its history. It might shift to quieter communication, use beams aimed elsewhere, or never develop radio technology at all. A signal that passes Earth before instruments are listening leaves no record. A signal that arrives outside the observed frequency range or from an unobserved direction may be missed. Even close stars require systematic attention across time, frequency, and signal type. The lack of evidence is real, but it is shaped by the narrowness of the search compared with the number of possible behaviors. In this region, the Fermi Paradox becomes less abstract and more observational. Nearby stars are counted, categorized, monitored, and revisited. Their planets are being discovered one by one. Their light is being measured for motion, dimming, color, and activity. Still, they do not reveal life easily. A living planet may look ordinary from far away. A quiet civilization may blend into natural radiation. A world with oceans may be hidden by clouds or by the angle of its orbit. A nearby star can be close in astronomy and still hold its planets behind layers of distance, glare, and incomplete information. The local stellar neighborhood therefore gives the paradox a measured shape. It does not show a galaxy filled with obvious signals. It does not show a galaxy proven empty. It shows a region where many stars are close enough to study, yet still too far for simple knowing. It contains common red dwarfs with difficult conditions, sun-like stars with uncertain planets, binary systems with varied stability, and remnants of older planetary histories. Around them, Possible worlds remain mostly unseen in detail. The silence here is more meaningful than silence from the far universe, because this is where the search can be most careful, yet it remains a silence bounded by instruments, timing, and the hidden nature of small planets around distant suns. Around nearby stars, the search moves inward from stellar neighborhoods to the planetary systems that surround them. These systems are no longer only ideas drawn from the solar system. They are observed in large numbers through changes in starlight, motion, timing, and sometimes direct images. An exoplanet is a planet outside the solar system, and thousands have been confirmed. They show that planet formation is a common outcome around stars, but they also show that planetary systems can be very different from the arrangement familiar around the Sun. This region is central to the Fermi Paradox because it changes the question from whether planets exist to what kinds of planets exist, how often they resemble Earth in useful ways, and how many remain hidden beyond current methods. The first lesson from exoplanet systems is variety. Some stars host giant planets close to their surfaces, orbiting in only a few days. These worlds are often called hot Jupiters, meaning gas giants heated strongly by tight orbits. Some stars host compact systems of several rocky or partly rocky planets, packed closer than Mercury is to the Sun. Some planets are larger than Earth, but smaller than Neptune, a size range not represented in the solar system by any planet. These worlds are often called super-Earths or sub-Neptunes, depending on their mass, radius, and likely composition. Their abundance shows that the solar system is not a complete template for all systems. It is one example among many outcomes. Planet detection methods shape what is known. The transit method finds planets when they pass in front of their stars and block a tiny portion of starlight. This method works best when the planet's orbit is aligned with Earth's view. The radial velocity method measures small shifts in a star's motion caused by the gravity of orbiting planets. This method works best for massive planets close to their stars, though improving instruments can find smaller effects. Direct imaging tries to separate the faint light of a planet from the glare of its star, which is easiest for large young planets far from their stars. Each method has strengths and gaps. The known catalogue of exoplanets is therefore not a perfect census. It is a map shaped by what instruments can most easily find. These detection limits matter to the Fermi Paradox because the most important worlds for life may be among the hardest to study. A small rocky planet in a temperate orbit around a sun-like star produces only a slight signal. Its transit may be rare and shallow. Its gravitational tug may be small. Its atmosphere, if present, leaves faint marks in starlight. A planet can be real and still remain undetected. It can be detected and still remain poorly understood. It can be known in size and orbit while its surface, air, water, and chemistry remain unknown. The search for aliens depends on moving through these layers of knowledge, and each layer becomes more difficult. Planetary systems also show that orbital architecture matters. Architecture means the arrangement of planets, their sizes, spacings, and paths around the star. Some systems have planets in nearly circular orbits. Others contain planets with more elongated paths. Some have resonances, where orbital periods relate in regular patterns because of gravitational interaction. Some systems may be dynamically calm for billions of years. Others may have undergone migration, scattering, or collisions. Habitability is not only a property of a single planet at one moment. It depends on whether the system around it remains stable enough for long climate histories. A rocky planet in a suitable orbit may still be affected by nearby giant planets, passing comets, or changes in orbital tilt. The formation of planetary systems begins in disks of gas and dust around young stars. Small particles collide, stick, grow, break, and gather again. Over time, larger bodies form. Some become rocky planets, some gather thick envelopes of gas, some remain as asteroids, comets, or icy bodies. The final system depends on the mass of the disk, its composition, the star's radiation, the timing of gas dispersal, and many gravitational interactions. This process creates diversity naturally. It also means that Earth-like conditions are not guaranteed by the mere presence of rock. A planet may form too close to the star and lose water. It may form too far out and freeze. It may gather too much gas and become a small Neptune-like world with no solid surface accessible to life as known. Water is a key uncertainty in exoplanet systems. Water appears common in cosmic chemistry, and ice can form in cold parts of planetary disks. But whether a rocky planet keeps surface water depends on where it forms, how it migrates, whether water-rich bodies deliver material later, how its atmosphere evolves, and how much radiation it receives from its star. Some planets may be dry from the beginning, some may be ocean worlds with deep global water layers and little exposed rock. Some may lose water to space if ultraviolet light breaks molecules apart and hydrogen escapes. The presence of water in a system is not the same as a stable ocean under a temperate sky. Atmospheres are equally uncertain. A planet may begin with gases from its formation disk, release gases through volcanoes, receive gases from impacts, or lose gases through stellar wind and radiation. A small planet close to an active star may struggle to keep a thick atmosphere. A larger planet may keep too much hydrogen and helium, forming a deep envelope unlike Earth's air. A stable atmosphere can moderate temperature, protect surfaces from harmful radiation, and allow liquid water under the right conditions. But atmospheres are difficult to measure for small planets. Most known exoplanets remain dots in data rather than worlds with known skies. The known variety of exoplanets softens some simple forms of the Fermi Paradox. Earlier thought often assumed that systems like the solar system might be common in familiar ways. Observations show that many systems are unfamiliar. This does not reduce the number of planets, but it reduces confidence that Earth-like arrangements are automatic. A star may have planets and still lack a stable rocky world with surface water. A system may have several planets and still place them too close to the star. A system may contain a potentially temperate planet around a red dwarf, but the star's activity and the planet's close orbit may create difficult conditions. The space between planet and habitable planet is broad. At the same time, exoplanet discoveries strengthen the paradox by confirming that planets are not rare. The galaxy is not mostly empty of worlds. Planet formation appears to accompany star formation often, even if only a fraction of planetary systems have stable rocky worlds. The total number in the Milky Way could still be very large. This creates the deep tension. There are many chances, but no confirmed life beyond Earth. The evidence has moved beyond speculation about whether other worlds exist. It has entered the harder stage of asking what those worlds are actually like, and whether any carry living processes or technological signs. The search across exoplanet systems remains young compared with the timescales involved. Instruments have begun to measure some atmospheres, especially around large planets and some smaller planets in favourable systems. Future observations may improve the ability to study rocky worlds. Still, every conclusion must remain careful. A molecule in an atmosphere may have living or non-living sources. A planet's size may suggest rock but not prove surface conditions. A temperate orbit may allow liquid water but not ensure it. Science advances by narrowing uncertainty, not by filling gaps with certainty. In this region, the Fermi Paradox is held inside those gaps. Exoplanet systems reveal a universe rich in worlds but not simple in meaning. They show planets close to stars, far from stars, in compact chains, in lonely wide paths, around small red stars, around sun-like stars, and around stars that have changed with age. They show that nature forms planets readily, but not according to a single design. The silence surrounding life beyond Earth therefore becomes more complex. It is not silence from a barren galaxy with few planets. It is silence from a galaxy where planets are common, while the conditions that make one planet living, stable, and detectable remain uncertain. In this inward region, the paradox rests among unseen surfaces, hidden atmospheres, and many worlds known first only by the faint shadows they cast across their stars. Inside the architecture of planetary systems, attention narrows to the region around a star where surface conditions might allow liquid water on a rocky planet. This region is often called the habitable zone. The term does not mean that life is present, and it does not mean that every planet there is gentle or Earth-like. It means that, with a suitable atmosphere and pressure at the surface, a planet could receive enough stellar energy for liquid water to exist without all of it freezing or boiling away. The habitable zone is therefore a first physical boundary, not a promise. In the Fermi Paradox, it is one of the places where abundance begins to narrow, because many planets may exist, but only some may orbit where surface water is possible under the right conditions. A star's brightness shapes the location of this zone. Around a bright star, the habitable zone lies farther out. Around a faint red dwarf, it lies much closer in. The amount of energy received by a planet depends on distance and on the star's output. A planet too close may absorb too much energy and enter a runaway greenhouse state, where water vapor strengthens warming and oceans can be lost. A planet too far away may freeze, unless greenhouse gases keep it warm enough. These boundaries are not sharp lines. They depend on clouds, atmospheric gases, surface reflectivity, rotation, continents, oceans, and the slow cycling of carbon through rock and air. Earth sits inside the Sun's habitable zone, but Earth is not habitable only because of its distance. Its atmosphere holds heat without trapping too much. Its surface pressure allows liquid water. Its rotation moves heat around the globe. Its oceans store energy. Its geology helps regulate climate over long times. A similar orbit around another star may not produce similar conditions if the planet's air is too thin, too thick, or made of different gases. Venus and Mars show the warning inside the same general planetary neighborhood. One becomes intensely hot beneath the dense atmosphere, and the other becomes cold and dry with thin air. Distance matters, but it is only one part of habitability. For red dwarf systems, the habitable zone lies very close to the star. This closeness creates both opportunity and difficulty. Because red dwarfs are common, their habitable zones may contain many planets across the galaxy. Yet planets so close to their stars may face strong flares, high-energy radiation, and stellar winds, especially early in the star's life. A close planet may also become tidally locked, with one side facing the star for long periods and the other side turned away. Models suggest that a thick enough atmosphere or ocean could move heat from day side to night side, but the outcome depends on details not yet known for most worlds. These systems widen the possible number of habitable zone planets while making their actual conditions uncertain. The lifetime of a star also matters. Massive bright stars have habitable zones far from the star, but their lives are short. they may not provide enough stable time for complex biological evolution as known on Earth. Smaller stars last far longer, but their early activity can be intense. Sun-like and slightly smaller stars may offer a balance between long lifetimes and moderate activity, though each star has its own magnetic history. Habitability, therefore, depends not only on where a planet is, but on how the star changes over time. A planet may begin in a suitable zone, later become too hot as the star brightens, or remain under difficult radiation during its early development. Atmospheric composition controls much of the habitable zone's meaning. Carbon dioxide, water vapor, methane, and other gases can warm a planet by absorbing outgoing heat. Clouds can cool a planet by reflecting starlight, or warm it by trapping heat, depending on the height, thickness, and distribution. Ice and snow reflect light strongly, which can push a cold planet toward deeper freezing. Dark oceans and rocks absorb more light. These feedbacks can stabilize or destabilize climate. A planet at the right distance may still become locked in global ice, a steam-filled greenhouse, or a dry state with no surface water. The habitable zone is therefore best understood as a region of possibility, filtered by climate. Geology adds another layer. On Earth, the long-term carbon cycle links air, ocean, rock, and volcanic activity. Carbon dioxide dissolves in rain and seawater, reacts with rock, becomes stored in minerals, and can return through volcanism. This process helps moderate climate over long periods. Whether other rocky planets have similar cycles depends on their size, internal heat, crust, volcanic activity, water inventory, and perhaps plate movement, plate tectonics. The motion of large pieces of a planet's outer shell may help recycle materials and stabilize climate, but its necessity for life remains uncertain. A planet without such movement may still have volcanism and chemistry, yet its long-term climate may follow a different path. The habitable zone also says little about the origin of life itself. Liquid water is important for life as known, because it supports chemical reactions, transports materials, and remains stable across a wide range of conditions. But water alone does not create biology. A planet may have oceans and remain lifeless. It may lack the right chemical pathways, energy sources, or environmental cycles needed for prebiotic chemistry to become living systems. The habitable zone marks where one major requirement may be met, not where life must appear. This distinction is essential to the Fermi Paradox, because the number of potentially habitable planets may be large, while the number of living planets remains unknown. Observations of habitable zone planets are difficult. Such planets are often small, faint, and close to their stars in the sky from Earth's viewpoint. Around red dwarfs, transits are easier to detect because the stars are small, but stellar activity can confuse signals and alter atmospheres. Around sun-like stars, Earth-sized planets in temperate orbits take about 1 year to circle, so repeated observations require long patience. Their atmospheres leave very weak marks. Current instruments can begin to study some favorable targets, but most habitable zone rocky planets remain beyond detailed atmospheric measurement. The most important category of planets for the Fermi Paradox is still one of the hardest to know. The habitable zone also changes with time. A young star may be dimmer or more active than in its mature period. A planet's atmosphere may thicken, thin, or change chemically. Water may be delivered, lost, stored underground, or frozen. Continents may rise or sink. Impacts may alter climates. Life itself, if it appears, may change the air, as photosynthesis changed Earth's atmosphere over long ages. Habitability is therefore not a permanent label fixed at formation. it is a history. A world can pass into and out of surface habitability as its star and planet evolve. In this region, the silence around Earth becomes narrower but not clearer. Many stars may have planets in or near their habitable zones. Some may be rocky, some may have atmospheres, some may have water. Yet each step from orbit to living surface adds uncertainty. The Fermi Paradox rests inside this narrowing sequence. Planets are common, but habitable zone planets are a subset. Habitable zone rocky planets are a smaller subset. Worlds with stable surface water for long spans may be smaller still. Worlds where life begins and becomes detectable may be rarer again. The size of each subset remains uncertain. The habitable zone is a calm idea with a difficult center. It is drawn from starlight, distance, climate, and water. But it does not contain life by definition. It is a margin around a star where one important condition may be possible, around countless stars. Such margins may exist as thin, temperate paths between heat and cold. Some may hold dry rocks. Some may hold frozen deserts. Some may hold oceans under clouds. Some may hold atmospheres that have already been lost to space, from far away. Most of them remain only measurements in light. In this inward region, the paradox becomes a study of narrow conditions, where the galaxy's many worlds must pass through the quiet filter of warmth, air, water, and time. Within the temperate margins around stars, the search moves down to the surfaces of rocky planets. A rocky planet is a world built mainly from silicate minerals and metal, with a solid outer shell rather than a deep envelope of hydrogen and helium. Such a surface gives chemistry a place to concentrate, separate, dry, dissolve, heat, cool, and repeat. It can hold oceans, lakes, ice, deserts, volcanoes, continents, basins, and shallow shores, depending on the planet's history. In the Fermi Paradox, this region is important because a planet may orbit in the right zone and still need a surface that remains stable and active long enough for life to begin, persist, and perhaps become complex. A rocky surface begins as heat and impact. Young planets form through collisions among smaller bodies. Their early crust can melt, break, reform, and become covered by lava or impact debris. Heavy material sinks inward to form a core, while lighter rock rises to make a mantle and crust. This separation is called differentiation. It shapes the planet's magnetic field, volcanic activity, and long-term heat flow. A surface suitable for life as known does not appear instantly. It must cool. It must hold or regain an atmosphere. It must allow water, if present, to remain in useful places. Early violence may deliver important materials, but too much violence can also remove air, boil oceans, or reset surface conditions. Water on a rocky surface can take many forms. It may cover most of the world as a global ocean. It may gather in smaller seas and lakes between continents. It may freeze into ice sheets or hide beneath crust. It may cycle through clouds, rain, rivers, and minerals. On Earth, water helps weather rock, move nutrients, regulate temperature, and provide a medium for living chemistry. But water alone is not enough. A deep ocean world with no exposed land may have less exchange between air, rock, and shallow surface environments. A dry world may have too little solvent for complex chemistry. A world with water only beneath ice may be protected from radiation, but harder to detect from space. Continents and shallow seas may matter because they create boundaries, coastlines, tidal pools, wet volcanic fields, mineral surfaces, and river deltas can concentrate chemicals and expose them to changing conditions. Drying and wetting cycles may help some prebiotic reactions, although the exact path to life remains uncertain. A planet entirely covered by deep ocean may still have chemistry at seafloor vents, where heated water moves through rock and carries dissolved minerals. A planet with too little water may have exposed rock but few stable liquid settings. The balance between land and water is therefore another filter, though science has not yet determined which surface arrangements are necessary or merely helpful. Geological activity keeps a rocky planet from being only a cooling stone. Internal heat drives volcanism, mountain building, crustal recycling, and chemical exchange between interior and surface. Volcanoes release gases that can build or renew atmospheres. Weathering can remove gases from air and store them in rock. Impacts can expose fresh minerals. Tectonic movement can reshape basins and continents. On Earth, these processes are tied to long-term climate stability and nutrient cycling. Another planet may have different forms of activity. It may have stagnant crust with occasional volcanism. It may have plates that move. It may have a thick outer shell that limits exchange. Each possibility changes the surface's ability to remain habitable. A planet's size influences its surface history. A very small rocky world may cool quickly, lose internal activity, and struggle to hold an atmosphere. A very large rocky world may keep heat longer and hold gases more strongly. But it may also develop high pressures, thick atmospheres, or different crustal behavior. Gravity affects mountains, oceans, air, and escape of gases to space. The right size is not known as a single value. Earth provides one example. Mars shows that a smaller world can once have surface water and later become cold and thin-aired. Venus shows that a similar-sized world can become extremely hot under a dense atmosphere. Size helps shape destiny, but it does not decide it alone. A magnetic field may help protect a planet's atmosphere from charged particles from its star. Although it is not the only factor in atmospheric survival, Earth's magnetic field is generated by motion in its liquid outer core. It guides many charged particles around the planet and helps form a protective space environment. Mars lacks a strong global magnetic field today and has lost much of its atmosphere over time, though its small size and gravity also matter. Venus lacks an Earth-like global magnetic field but still has a dense atmosphere. These examples show that protection is complex. A magnetic field can be helpful, but atmosphere, gravity, star activity, and chemistry all act together. Surface climate depends on many linked features: the amount of starlight, the thickness of the atmosphere, the rotation rate, the tilt of the axis, the pattern of oceans and continents, and the presence of clouds all matter. A planet with a strong tilt may have extreme seasons. A planet with little tilt may have stable climate zones. A planet spinning slowly may distribute heat differently from one spinning quickly. Mountains can change winds and rainfall. Ice can reflect sunlight and spread cooling. Clouds can shade or warm. Climate is therefore a moving system, not a fixed number. For life to endure near the surface, conditions may need to remain within useful ranges over long spans, though microbial life can survive difficult extremes. The surface also faces hazards from space. Asteroid and comet impacts can deliver water and organic molecules, but large impacts can melt crust, darken skies, heat atmospheres, and disrupt oceans. A young planetary system often has more debris, while older systems may become calmer. Nearby supernovae, strong stellar flares, and changes in stellar output can affect surface radiation. An atmosphere, ocean, ice layer, or underground setting can reduce some hazards. Life, if it begins. may first survive in protected environments before spreading more widely. The surface is open to the sky, and that openness brings both energy and risk. Detection of planetary surfaces remains extremely hard. For most exoplanets, no image of the surface exists. Astronomers infer surface possibility from mass, radius, density, orbit, and sometimes atmospheric clues. A rocky density may suggest a solid world, but it does not reveal oceans or continents. A planet's reflected light may one day show color changes, cloud patterns, or hints of rotation, but such measurements are demanding. Even Earth seen from far away would be only a faint point beside the Sun. Its oceans, clouds, vegetation, deserts, and ice would blend into subtle changes in brightness and color. A living surface can be obvious up close and nearly invisible across interstellar distance. The Fermi Paradox becomes more grounded at the surface because life as known is not a property of stars or orbits alone. It is tied to places where matter interacts in many forms over time. Rock must meet water, air must meet light, heat must move through crust, chemicals must gather and react, stability and change must coexist. Too much stability can limit chemical renewal, too much change can erase fragile beginnings. A planet's surface must be active enough to supply materials and steady enough to preserve them. This balance may be common, or it may be rare. Current evidence does not settle the matter. Rocky planets may be numerous in the galaxy, but the number with long-lived, life-friendly surfaces remains unknown. Some may be dry stones, some may be cloud-covered greenhouses, some may be frozen under dim stars, some may hold oceans below ice, some may carry air that changes in ways not yet measurable. The absence of confirmed alien life is therefore not a silence from known Earth-like surfaces everywhere. It is a silence from mostly unseen surfaces whose histories are still hidden. In this inward region, the paradox rests on ground that cannot yet be walked, under skies that cannot yet be directly seen, across worlds where rock, water, heat, and time may or may not have made a place for life. Above the surface of a rocky planet, the atmosphere becomes the next inward layer of the search. An atmosphere is a blanket of gas held by gravity, shaped by the planet's size, temperature, chemistry, geology, and star. It can warm a surface, cool a surface, shield it from harmful radiation, move water, carry clouds, and record chemical changes from far away. An atmosphere may be the first part of a planet that becomes measurable, because starlight can pass through it or reflect from it. In the Fermi Paradox, this region is important because life may be hidden on a distant surface, but its gases could leave a faint sign in the light that reaches telescopes. A planet's air begins with formation and change. Some gases may come from the original disk around the young star. Some may be released from rock through volcanism. Some may arrive with comets and asteroids. Some may be removed by impacts, radiation, chemical reactions, or escape into space. The final atmosphere is not fixed at birth. It evolves across time. Earth's air changes greatly over its history, especially after photosynthetic life begins producing oxygen. Venus, Earth, and Mars show very different results from planets in the same general solar system region. Venus keeps a dense carbon dioxide atmosphere and becomes extremely hot. Mars loses much of its early atmosphere and becomes cold and thin-aired. Earth keeps a surface pressure and composition that allow oceans and life to persist. For astronomers, gases can become clues. A biosignature is a possible sign of life, often a chemical pattern that may be difficult to explain without biology. Oxygen, ozone, methane, nitrous oxide, and certain combinations of gases may draw attention. But no single gas is always proof. Oxygen can be produced by life, but non-living processes may also create it under some conditions. Methane can come from living systems, but it can also come from geology. A strong biosignature depends on context. The star's radiation, the planet's temperature, the presence of oceans, the balance of other gases, and whether non-living explanations can be ruled out. The atmosphere can speak, but its language is not simple. A technosignature is a possible sign of technology. In an atmosphere, this might include artificial chemicals that are unlikely to form naturally in large amounts, or heat patterns suggesting large-scale energy use. These ideas remain difficult to test. Detecting small quantities of unusual gases across interstellar distance requires sensitive instruments and favorable planets. Natural processes can imitate many patterns. A careful scientific claim requires more than surprise. It requires repeated observations, strong data, and a clear understanding of possible non-living sources. No atmospheric technosignature has been confirmed beyond Earth. The method of studying exoplanet atmospheres often depends on transits. When a planet passes in front of its star, a small amount of starlight filters through the planet's upper atmosphere. Molecules absorb certain wavelengths, leaving marks in the spectrum. A spectrum is light spread by wavelength, revealing colors and invisible bands that carry chemical information. This method is strongest for large planets with puffy atmospheres and for planets around smaller stars, where the signal is less overwhelmed by the star. Small rocky planets are much harder. Their atmospheres are thin compared with the size and brightness of their stars. The most interesting worlds may leave marks near the edge of present detectability. Another approach studies reflected or emitted light from a planet. Reflected light carries information about clouds, surface brightness, and atmospheric gases. Emitted heat can reveal temperature and energy balance. Directly measuring this light is difficult because a planet is faint beside its star. Future instruments may improve the ability to block starlight and isolate planetary light. Even then, interpretation remains careful. Clouds may hide surface features. Haze may block deeper layers. A planet with life might not show an obvious signal, and a planet without life might show gases that seem suggestive until its full context is understood. Atmospheres also determine whether surface life is visible from afar. If a planet has no air, its surface may be exposed to radiation and extreme temperature swings. If it has too much air, pressure and heat may make the surface hostile to life as known. If its atmosphere is thick with clouds, the surface may be hidden even if oceans exist below. If its air is thin but stable, liquid water may be limited. The same atmosphere that protects life can also conceal it. A distant observer may detect only the top of clouds or the chemistry of high air, not the living systems below. Clouds and hazes are especially important. They reflect starlight, trap heat, and alter spectra. A cloudy planet may appear brighter than a clear one. Haze can form from chemical reactions driven by ultraviolet light. Such particles can shield a surface from radiation, but they can also make atmospheric gases harder to identify. On early Earth, haze may have played roles in climate and chemistry, depending on atmospheric conditions. On exoplanets, clouds and hazes are often uncertain. They can flatten spectral features, making gases harder to detect. This means a living world might be misread as featureless, not because it lacks air, but because its air hides its own details. The star's light controls much of atmospheric chemistry. Ultraviolet radiation can break molecules apart. Stellar winds can remove upper atmospheric particles. Flares can change chemistry and increase escape, especially around active red dwarfs. At the same time, Some high-energy light can drive chemical reactions that may be useful for prebiotic processes. The effect depends on strength, timing, atmosphere, magnetic protection, and planetary gravity. A star and atmosphere form a coupled system. A gas that remains stable around one star may be destroyed quickly around another. A biosignature must therefore be judged with the star included, not as an isolated molecule. Earth's atmosphere gives a reference point, but also a warning. For much of Earth's history, life exists without producing an atmosphere that modern observers would easily recognize as strongly oxygen-rich. Microbial life may alter gases subtly for long periods. Complex life appears much later. A distant telescope looking at Earth at different ages might draw different conclusions. This matters for the Fermi Paradox because living worlds may be common but not always visible through strong atmospheric signs. A planet may have life beneath oceans, under ice, in rocks, or in microbial mats without producing a clear global signal. Life can be real and still quiet. The search for atmospheric signals is also limited by time. Observations require repeated measurements, stable instruments, and careful separation of planetary light from stellar activity. A star's spots, flares, and changing brightness can imitate or obscure planetary features. Instruments must account for noise from Earth's own atmosphere when observations are ground-based, or from telescope systems when observations are in space. A possible detection may remain uncertain for years while further data are gathered. Science moves cautiously because false positives are possible, and because the meaning of a gas depends on many connected facts. In this region, the Fermi Paradox becomes a problem of interpretation as much as distance. The galaxy may contain planets with atmospheres, but an atmosphere is not a simple label. It is a moving chemical system. It can preserve life, erase life's traces, or produce misleading patterns without life. It can reveal oxygen, methane, water vapor, carbon dioxide, or haze. But each finding must be placed into a planetary story. A silent atmosphere may not be lifeless. A suggestive atmosphere may not be living. The space between measurement and conclusion remains wide. Above distant surfaces, atmospheres hold the faint traces that telescopes seek. They are thin compared with planets, and almost invisible beside stars, yet they carry the possible marks of oceans, volcanoes, sunlight, chemistry, and biology. They may be the first places where life beyond Earth is recognized, or they may deepen the uncertainty by showing signals that remain ambiguous. The silence of the Fermi Paradox is therefore not only an absence of messages, it is also the difficulty of reading air across light years. In this inward region, the search rests in the delicate outer skin of worlds, where gases move, clouds form, starlight changes, and possible life leaves marks too faint to be certain. Beneath air and weather, the search for life reaches the chemical threshold where non-living matter may begin to organize into living systems. This region is not a single place on a planet and not a known step with a complete explanation. It is the boundary between chemistry and biology, where simple molecules become linked into more complex networks that can store information, use energy, and copy themselves with variation. Life on Earth proves that this transition can happen at least once, but science does not yet know exactly how it happened. In the Fermi Paradox, this threshold is one of the deepest uncertainties, because many planets may have water, rock, and air, while only some may cross from chemistry into life. Prebiotic chemistry is chemistry before life. It includes reactions that make organic molecules, which are carbon-based molecules important to living systems. Organic molecules can form in many natural settings. They have been found in meteorites, in interstellar clouds, and in laboratory experiments that imitate some planetary conditions. Amino acids, simple sugars, bases related to genetic material, and fatty molecules can arise through non-living processes under certain conditions. This does not mean that life is easy to start. It means that some of life's ingredients are not unique to living organisms. The harder question is how ingredients become organized into a system that can persist, reproduce, and evolve. Life as known uses molecules that perform linked roles. Nucleic acids store genetic information. Proteins act as catalysts and structures. Lipids form membranes that separate an inside from an outside. Metabolism moves energy and matter through chemical pathways. These features support one another in modern cells. But that creates a puzzle for origins. A cell uses many parts together. Early life must have begun with simpler systems. Scientists study possible paths such as an RNA world, where ribonucleic acid may have stored information and helped catalyze reactions before modern DNA and protein systems became dominant. This idea has evidence and challenges. It remains a field of active research rather than a finished account. A chemical threshold likely requires concentration. In a vast ocean, useful molecules can become too diluted to interact often. Local environments may gather and cycle materials, shallow ponds, wet and dry volcanic fields, mineral surfaces, ice pockets, hydrothermal vents, and porous rocks have all been studied as possible settings. Minerals can provide surfaces that hold molecules close together. Drying can bring molecules into contact. Heating and cooling can drive reactions. Chemical gradients, such as differences in acidity or electrical charge, can provide energy. No single setting has been proven as the actual origin of life on Earth. Each offers some useful conditions and some difficulties. Hydrothermal vents provide one possible environment. These are places where heated water flows from the seafloor, carrying dissolved minerals and energy. Some vents create natural chemical gradients between alkaline fluids and more acidic ocean water. Such gradients resemble, in a broad way, energy differences used by living cells. Porous mineral structures could have helped concentrate molecules and support reactions. This setting has appeal because it combines water, rock, heat, and chemical energy. It also faces questions about how early informational molecules would form and remain stable in such environments. The vent idea is important, but it is not a complete solution. Surface pools and wet-dry cycles provide another possible route. In shallow settings, water can evaporate and return. Molecules can become concentrated during drying and then move again when water returns. Some reactions that build longer chains of molecules work better when water is temporarily removed, even though life later needs water. Such cycles may have occurred on volcanic land, near hot springs, or in impact-shaped basins. This setting depends on exposed land and climate conditions. It may not apply to ocean worlds without continents. If such cycles were important for life's origin, then worlds covered entirely by deep water might face different challenges. Membranes are another key step. A living system needs some boundary that keeps useful molecules together while allowing exchange with the environment. Fatty molecules can sometimes form simple vesicles, tiny enclosed structures with membrane-like walls. These vesicles can grow, divide, and hold chemicals under laboratory conditions. They are not alive by themselves, but they show how natural boundaries can form. A boundary allows a chemical system to have an inside, where reactions can become linked and selected. Without boundaries, successful chemical arrangements may drift apart. With boundaries, some collections of molecules may persist longer than others. Energy must flow through early systems, Life is not just a collection of molecules. It is matter kept away from simple equilibrium by energy use. Sunlight, geothermal heat, chemical reactions, and electrical energy can all drive changes. On Earth today, living organisms use complex metabolic pathways, but early systems likely use simpler energy sources. A planet may contain organic molecules and water, but if energy is unavailable in useful forms, organization may stall. If energy is too intense, molecules may be destroyed faster than they form. The threshold requires not only ingredients and water, but energy at a level and pattern that supports complexity. Information is equally important. For evolution to begin, a system must make copies with differences that affect survival or reproduction. Modern DNA is highly effective, but too complex to assume at the start. RNA can store information and perform catalytic roles, which is why it receives close attention. Other chemical systems may also have played roles before modern biology. The origin of heredity remains one of the central problems. Without heredity, chemistry may become complex but cannot accumulate improvements in the Darwinian sense. With heredity, even a simple system can begin a long process of change, adaptation, and increasing organization. The time required for life to begin is uncertain. Earth forms about 4.5 billion years ago, and evidence suggests life exists by at least more than 3.5 billion years ago, with some possible signs older but debated. This may imply that life began relatively early once Earth became suitable, or it may reflect the loss of older rocks and the difficulty of preserving evidence. A quick origin on Earth could mean the transition is common under the right conditions, or it could be a rare event that happened early by chance. One example cannot reveal the probability. This uncertainty sits at the heart of the Fermi Paradox. Another uncertainty is whether life must resemble Earth life. Science can study life only as it is known, based on carbon chemistry, water, cells, and genetic systems. Carbon is chemically versatile, and water is an excellent solvent, so these may be broadly useful. Still, the search remains cautious. Life elsewhere might differ in details while still requiring organization, energy flow, and heredity. It might use different molecules for related roles, yet without evidence. Science cannot assume exotic alternatives. The most reliable approach begins with conditions known to support life, then expands carefully where chemistry allows. If the chemical threshold is easy to cross, then life may be common across many habitable worlds, even if intelligence remains rare. If the threshold is difficult, then the galaxy may contain many wet, rocky, chemically rich planets that remain lifeless for billions of years. This distinction strongly affects the Fermi Paradox. The silence may not require civilizations to fail later if life seldom begins. Or life may begin often, while later steps are the true filters. Current evidence does not identify which stage is most limiting. The origin of life remains both a scientific frontier and a key unknown in estimating the abundance of aliens. At this inward layer, the question becomes very small in scale while staying cosmic in meaning. It concerns molecules meeting on mineral surfaces, droplets drying and filling again, pores in warm rock, gases entering water, and chains of atoms copying imperfectly. These events, if they occur, are not bright across space. They do not send signals. They do not alter a planet instantly. They begin below visibility, in chemistry that may persist unnoticed for immense periods. The Fermi Paradox may therefore depend on processes no telescope can watch directly on distant worlds. In this region, the silence of the universe reaches into the quiet difficulty of matter learning, through natural chemistry, to become alive. After life begins, this urge moves inward through the long biological gates that separate simple living systems from complex organisms and intelligence. A planet with microbes is not the same as a planet with animals, forests, tools, or signals on Earth. Life appears to remain microscopic for most of its history. Cells become established, adapt to many settings, and alter the planet slowly. But complex multicellular organisms arise much later. This long delay matters to the Fermi Paradox because life may be widespread while complex life remains uncommon. The silence of the galaxy may come not from the absence of biology, but from the difficulty of passing through several slow and uncertain evolutionary transitions. The first living systems are likely simple compared with modern cells. Over time, life diversifies into microbes that use different sources of energy and matter. Some organisms draw energy from sunlight, others use chemical reactions involving minerals, gases, or organic material. Microbial life can live in hot springs, deep rocks, ocean vents, salty lakes, ice, and ordinary soils. Its resilience shows that once life is established, it can occupy many environments. This resilience may make microbial life a strong possibility on suitable planets. Yet microbes can remain microbes for billions of years. They do not automatically build large bodies, nervous systems, or technology. One major transition on Earth is the rise of oxygen-producing photosynthesis. Photosynthesis is the use of light energy to build chemical energy, and some forms release oxygen as a waste product. Over long periods, oxygen accumulates in Earth's atmosphere and oceans, though not immediately. At first, oxygen reacts with minerals and dissolved substances. Later, it becomes more abundant in the air. This change transforms Earth's surface environment. Oxygen allows more efficient energy use in many organisms, but it is also reactive and harmful to life not adapted to it. The oxygenation of a planet may therefore be both a crisis and an opportunity. Its timing and scale can shape later evolution. Complex cells are another deep gate. Earth life includes prokaryotic cells, which are simpler cells without internal compartments like a nucleus, and eukaryotic cells, which have more complex internal structures. Eukaryotic cells appear to have emerged through a profound partnership between earlier cells. Mitochondria, the energy-producing structures in animals, plants, and many other organisms, descend from bacteria that became integrated inside another cell. This endosymbiosis is a rare and complex event in Earth's known history. It may have allowed cells to manage energy in ways that supported larger genomes, internal organization, and later multicellular life. Whether such an event is common on other planets remains unknown. Multicellularity is the next gate. It means cells living together in coordinated bodies, with different cells taking different roles. Multicellularity has evolved more than once on Earth in broad forms, including plants, animals, fungi, and some algae. This suggests that cooperation among cells can arise repeatedly under some conditions. Still, large complex multicellular life requires more than cells sticking together. It requires development, communication, structure, nutrient transport, reproduction, and control over growth. A planet might have microbial mats and simple colonies without producing large organisms. The path from single cells to bodies with tissues and organs may depend on oxygen levels, ecological pressure, genetic tools, and stable environments. The history of Earth also includes long intervals when life changes without producing technological intelligence. For billions of years, there are no animals. Later, animals diversify in oceans. Some eventually move on to land. Plants reshape continents. Insects, fish, reptiles, mammals, and birds appear through branching evolution, extinction, and adaptation. None of these stages has a predetermined direction toward intelligence. Evolution does not aim at technology. It responds to local conditions through variation and selection. Traits that help survival and reproduction in one setting may not lead toward large brains or tool use. This matters because intelligence cannot be assumed as the natural endpoint of life. Nervous systems arise as organisms interact with their surroundings. Sensing light, chemicals, touch, and motion can help animals find food, avoid danger, and reproduce. More complex nervous systems allow flexible behavior, learning, and memory. Yet many successful organisms thrive without large brains. Bacteria, plants, fungi, insects, and simple animals can survive and reproduce in vast numbers. Large brains are costly. They require energy, long development, and protection. A planet with complex life may still never produce a species that builds instruments or sends signals. Evolution may favor speed, shells, venom, camouflage, cooperation, or endurance rather than technological thought. Intelligence itself has many forms. On Earth, problem-solving, memory, social learning, and communication appear in different degrees among several animals. Octopuses, crows, dolphins, elephants, primates, and other organisms show complex behavior. Human technological civilization arises from a specific lineage with hands, social groups, language, culture, fire use, and cumulative learning. This combination is not merely a large brain. It includes anatomy, environment, social transmission, and access to materials. A world could produce intelligent ocean animals without fire or metallurgy. It could produce tool-using land animals without developing radio technology. Intelligence and detectability are related, but not identical. Mass extinctions and environmental disruptions also shape the path. Earth's history includes major losses of biodiversity caused by impacts, volcanism, climate change, ocean chemistry shifts, and other factors. These events destroy many lineages while opening space for others. Without the extinction of many dominant reptiles, mammals may not have diversified in the same way. Such contingency means that evolutionary outcomes depend on chance events as well as broad laws. A planet can be habitable and life-bearing, yet its history may follow countless possible routes. Some routes may never lead to a technological species, others may do so only briefly. Time is a central filter. Earth takes billions of years to produce a technological civilization after life begins. This long timescale must fit within the stable lifetime of the star and planet. Around short-lived stars, there may not be enough time. Around long-lived red dwarfs, there may be time. But early stellar activity and planetary conditions may create other difficulties. A stable climate must persist through geological change. Oceans must remain. Atmospheres must not be lost or transformed beyond recovery. Biological innovation must occur within the window that the planet remains suitable. Long time helps evolution, but it also gives more chances for disruption. The Fermi Paradox becomes especially subtle at this layer because every step is known from only one planet. Earth shows that life can become complex and technological, but it does not show how likely that path is. Some transitions, such as simple multicellularity, may be relatively common once life is established. Others, such as the origin of eukaryotic cells or technological intelligence, may be rare. Science cannot yet assign reliable probabilities. It can only identify the steps and compare them with evidence from Earth's deep history. The silence of the galaxy may reflect one very hard step or many moderately hard steps combined. This biological inward region changes the meaning of aliens. It suggests that the galaxy, if living, may be mostly microbial. Planets may breathe with invisible chemistry, host oceans full of simple cells, or carry films of life across rocks and sediments without ever making voices or machines. Such worlds would not answer signals. They would not build transmitters. Their existence might be detectable only through atmospheric chemistry, and even that could be uncertain. The absence of technological contact would then tell little about the abundance of life itself. It would speak more about the rarity of complex, tool-making organisms. Within evolutionary history, silence is not empty. It is time moving through cells, mutations, extinctions, and slow environmental change. A living planet may remain quiet for ages, not because it fails, but because life has no reason to announce itself. Microbes divide, oceans circulate, rocks weather, oxygen rises or falls. Bodies become more complex only if conditions and chance allow. Intelligence appears only if many earlier gates have opened. In this region, the Fermi Paradox rests on the long patience of biology, where life may begin in small chemical systems and then spend most of a planet's history without ever becoming detectable across the stars. After complex life and intelligence, the search moves inward to the narrow interval in which a civilization becomes technological enough to produce detectable signs. A civilization is not only a population of intelligent beings, it is a system of shared knowledge, tools, energy use, communication, memory, and social organization. On Earth, such a system appears very late in the planet's history. Radio technology appears later still, after most of life's story has already passed. This timing matters deeply to the Fermi Paradox because a planet may host life for billions of years, complex organisms for hundreds of millions of years, and technology for only a brief visible span. The universe may contain many living histories whose detectable windows rarely overlap. A communication window is the period when a civilization sends signals that another civilization could notice. This window may be short or long, loud or quiet, accidental or deliberate. Human radio leakage has existed for only a small fraction of a century on geological timescales, and much of it weakens rapidly with distance. Powerful directed transmissions are different from ordinary leakage, but they require intention, energy, and a target or survey plan. A civilization might use radio for a while and later shift to communication methods that leak less energy into space. It might communicate through cables, narrow beams, or technologies not easily detected from afar. Detectability is therefore not the same as intelligence. Timing creates a severe filter. Two civilizations may exist around nearby stars and still miss each other if their technological periods do not overlap. One may rise millions of years before the other. Its signals may pass through space before the second has instruments. It may disappear, change, or stop transmitting long before a reply could return. Across the galaxy, light travel times are measured in years, centuries, millennia, and longer. Communication is delayed even between relatively close stars. A message is not a meeting, it is a fossil of activity, moving outward through space after the sender has already entered a different future. The lifetime of technological civilizations is unknown. Earth provides no long record, because human technology is new. A technological species may last for a short time if it destroys its environment, suffers war, loses industrial capacity, or fails to manage its own power. It may last for a long time if it becomes stable, cautious, and adaptable. It may spread beyond its home world, or it may remain local. It may choose to transmit, or it may choose silence. None of these outcomes is known from evidence beyond Earth. The Fermi Paradox becomes uncertain here because the most important number may not be how often intelligence appears, but how long it remains visible. Energy use can create detectable traces, but only at large scales. A young technological civilization may alter its planet's atmosphere, light patterns, radio environment, or heat balance. Industrial gases may leave chemical marks. Artificial lights may brighten a night side. Large energy systems may produce waste heat. Yet these signs are extremely faint across interstellar distance, unless the civilization uses energy on a scale far beyond current humanity, or unless the observing instruments are very advanced. A modest civilization could be real and still nearly invisible. It could use technology in ways that blend into natural planetary signals. The idea of advanced civilizations sometimes leads to imagined megastructures, such as vast collectors of stellar energy. In scientific terms, such possibilities are considered as techno-signature targets only if they produce observable effects, such as unusual infrared excess or abnormal dimming of starlight. But natural explanations must be examined first. Dust clouds, young planetary disks, stellar activity, and background objects can imitate strange signals. A claim of technology requires evidence that survives ordinary astrophysical explanations. So far, no such claim has been confirmed. The lack of detected megastructures suggests that if advanced civilizations exist, they are not common in forms that are easy to see, at least within searched regions and sensitivities. Expansion through space is another uncertain step. A technological civilization might send probes, colonies, or self-replicating machines. If such expansion were easy, common, and long-lasting, the galaxy might show signs of widespread engineering or visitation. The absence of confirmed evidence raises questions, but interstellar expansion may be far harder than simple models assume. Distances are immense. Travel requires energy, shielding, reliability, and long-term purpose. Biological beings may not survive easily between stars. Machines may fail, drift, or be deliberately limited. A civilization may have no reason to expand aggressively. It may prefer stability near its home star or within its own system. Motivation cannot be measured from Earth. A civilization may be curious, cautious, indifferent, inward-looking, or constrained. It may not share human assumptions about exploration, growth, or communication, even on Earth. Cultures and institutions differ in how they use technology and how they value risk. Across another biosphere, intelligence could produce social patterns that are difficult to imagine and impossible to infer without evidence. Science cannot use imagined motives as proof. It can only note that detectability depends not only on capability, but also on behavior. A civilization that can transmit may not transmit. A civilization that can travel may not travel. There is also the possibility of non-simultaneity on a galactic scale. The Milky Way is more than 10 billion years old. Earth's technological period occupies only the latest instant in that span. Other civilizations, if they arise, may be separated from humanity by millions or billions of years. Some may have existed before Earth had complex life. Some may arise long after humanity is gone. The galaxy is not a stage on which all possible civilizations appear at the same time. It is a long sequence of worlds forming, changing, and ending under different stars. The silence may reflect time spread too thinly across space. Self-destruction is often discussed as one possible filter, but it must be treated carefully. Human history shows that technology can create risks, including warfare, environmental damage, and powerful tools used without foresight. It also shows learning, cooperation, and the ability to reduce some dangers through knowledge. No evidence shows that all technological civilizations destroy themselves. No evidence shows that they usually survive. The idea remains a hypothesis, not a conclusion. It matters because even a small chance of failure at each stage may shorten average detectable lifetimes. A galaxy with many brief civilizations could still appear quiet most of the time. Long-lived civilizations may also become less visible. A stable advanced society might use energy efficiently, avoid waste, reduce leakage, and communicate through tightly directed channels. It might design systems that do not produce obvious signals. It might live in ways that resemble natural background processes from a distance. Detectability may peak during a transitional period when technology is powerful but not yet quiet. If that period is short, searches for accidental signals become difficult. The loudest phase may not be the longest phase. The Fermi Paradox often assumes that intelligence wants to be found, but science cannot assume that. Deliberate messaging requires a decision to send information into space, often without knowing who may receive it or when. Some may see value in such messaging. Others may avoid it. A civilization may listen more than it speaks. It may send only to known targets. It may communicate through methods not chosen by human searches. The absence of messages could come from rarity, caution, weakness, directionality, timing, or simple distance. Each possibility remains open because no confirmed comparison exists. In this inward region, the paradox becomes less about planets and more about clocks. Biological clocks, cultural clocks, technological clocks, and light travel clocks must align. A planet must produce intelligence. Intelligence must build detectable technology. The detectable phase must last. Its signals must cross space while another civilization is listening with suitable instruments. The signal must be strong enough, clear enough, and recognized as artificial. Each condition narrows the chance of contact without requiring the universe to be empty. The silence may be the result of many windows opening and closing in the dark without facing one another. Civilizations, if they exist elsewhere, may be brief sparks, long quiet embers, or enduring systems that do not announce themselves. They may rise under red stars, around sun-like stars, on ocean worlds, or on continents beneath unfamiliar skies. They may never use radio. They may use it and stop. They may listen and hear nothing, as Earth does. From this layer, the Fermi Paradox becomes a study of overlap. The galaxy may contain minds that are separated not only by distance but by era, behavior, and the limits of signal strength. In this region, the silence is not simple absence. It is the thinness of shared time across a vast and slowly turning galaxy. Even if civilizations exist and produce signals, the ability to detect them depends on instruments, methods, and limits that define what can be seen or heard across space. This inward region focuses on detection itself, the tools and strategies used to search for signs of life and intelligence. The Fermi Paradox is shaped not only by what exists in the universe, but also by what current science can measure. A quiet sky may reflect absence, or it may reflect the boundaries of observation. Where signals remain too faint, too rare, too brief, or too unfamiliar to be recognized. Radio searches have been among the most direct methods. Radio waves travel through interstellar space with relatively little absorption, and they can be produced by natural sources as well as technology. Telescopes scan selected stars or regions of the sky, looking for narrow-band signals or patterns that differ from known natural emissions. A narrow-band signal is one concentrated in a very small range of frequencies, which is uncommon in nature. Such signals can stand out against the broader noise of cosmic sources. However, the search covers only a small fraction of the sky, a limited range of frequencies, and specific times. A signal could exist outside these ranges, arrive at a different time, or be too weak to detect. The absence of detection does not mean that no signals exist anywhere. It means none have been confirmed within the search space of frequency, direction, and duration. Optical searches look for pulses or patterns of visible or near-visible light that might indicate technology. A powerful laser pulse could, in principle, outshine a star for a brief moment in a narrow beam. Instruments monitor stars for unusual flashes that differ from known astrophysical events. As with radio searches, the challenge lies in coverage. Only certain stars can be monitored at any time, and only certain patterns can be recognized against natural variability. A civilization might not use optical signals, or it might aim them in directions not aligned with Earth. Detection depends on both the sender's method and the observer's expectations. Infrared observations offer another path by searching for excess heat. Any use of energy produces waste heat that must be radiated away. A very large-scale technological system might alter the infrared signature of a star or a planetary system. Surveys can look for objects with unusual heat patterns that do not match standard models of dust, gas, or stellar processes. Yet natural phenomena can also produce infrared excess, especially in young systems with dust disks or in regions with complex gas clouds. Interpreting such signals requires careful modeling and comparison with known astrophysical behavior. No clear techno-signature has been confirmed through this method. The search for biosignatures in atmospheres also falls under detection limits. As instruments improve, astronomers can begin to measure the chemical composition of some exoplanet atmospheres. They look for gases that might indicate biological activity. However, signals are faint and interpretation is uncertain. A planet's atmosphere may be observed at only a few wavelengths with limited resolution. Clouds and haze can obscure deeper layers. Stellar activity can mimic or distort signals. A detection may suggest a possibility rather than provide proof. Confirmation requires repeated observations, different methods, and strong exclusion of non-living explanations. Distance reduces signal strength. A signal spreads out as it travels, becoming weaker with distance. This is known as the inverse square effect, where intensity decreases with the square of the distance. A signal that is strong near its source may become undetectable after traveling many light years. Even powerful transmissions weaken as they spread. Directed beams can reduce this effect by focusing energy, but they must be aimed. An untargeted broadcast disperses quickly. This means that civilization must either transmit with great power, aim carefully, or be close enough for its signals to be noticed. Most of the galaxy remains beyond easy reach for current detection sensitivity. Time also limits detection. Signals may be continuous, periodic, or brief. A short-lived signal can be missed if instruments are not observing at the right moment. A repeating signal may be mistaken for natural periodic phenomena such as pulsars, which produce regular radio pulses. A one-time event may be indistinguishable from noise unless recorded and analysed carefully. Observatories must decide where to look and how long to observe. balancing limited time among many targets. The sky is large, and observation time is finite. Coverage is therefore incomplete by necessity. Noise complicates every search. The universe produces a wide range of natural emissions across the electromagnetic spectrum. Stars flare, gas clouds emit, dust glows, and compact objects produce intense radiation. Earth itself contributes noise through its atmosphere and human-made signals. Distinguishing an artificial signal from this background requires careful filtering, modeling, and verification. False positives can arise from instrument effects, interference, or misunderstood natural sources. Scientific standards require that a candidate signal be repeatable or strongly supported before it is accepted. Many intriguing signals have been investigated and later explained or not confirmed. Search strategies are shaped by assumptions. Some searches focus on sun-like stars, others on red dwarfs, others on regions with many stars. Some scan wide areas briefly, while others study specific targets in detail. Frequency choices reflect ideas about where a civilization might transmit. These choices are reasonable but limited. A civilization may choose frequencies or methods not anticipated. It may encode information in ways not recognized as artificial. Detection depends on matching unknown behavior with known search patterns. The gap between expectation and reality can hide signals even if they are present. There are also physical limits to observation. Telescopes have finite size, sensitivity, and resolution. Space-based instruments avoid some atmospheric interference but still face engineering constraints. Future observatories may improve detection of small planets, faint atmospheres, and subtle signals, but no instrument can remove all limits. The speed of light sets a boundary on how quickly information can arrive. The expansion of the universe limits contact with very distant regions. Even with perfect instruments, some parts of the cosmos remain effectively unreachable. The Fermi Paradox, at this stage, becomes a question about the space searched versus the space available. The Milky Way contains hundreds of billions of stars. Only a small fraction have been examined in detail for technosignatures. Even among nearby stars, coverage is incomplete. The search has begun, but it remains in an early phase relative to the scale of the task. The silence observed so far is therefore a measurement within a limited survey, not a final statement about the galaxy. The concept of a search space is useful here. It includes all directions in the sky, all frequencies, all times, all signal types, and all levels of sensitivity. Current searches cover only a small portion of this space. Expanding coverage increases the chance of detection if signals exist. However, expanding coverage requires time, resources, and new technology. The search is gradual, building knowledge step by step. Each observation reduces uncertainty slightly, even when no signal is found, because it defines where signals are not detected under certain conditions. Detection is also influenced by interpretation. Recognizing a signal as artificial requires understanding natural phenomena well enough to rule them out. Astronomy has repeatedly discovered unexpected natural sources that at first appear unusual. Pulsars were once considered possible artificial signals before their natural origin was understood. This history encourages caution. A true technosignature must stand apart from all known natural explanations. Until such a signal is found and confirmed, the silence remains a combination of non-detection and careful scientific restraint. In this region, the Fermi Paradox reflects the limits of knowledge as much as the state of the universe. Instruments listen and watch, but they do so within narrow bands of possibility. Signals may exist outside those bands, below detection thresholds, or in forms not yet recognized. The absence of evidence is shaped by where and how science looks. The galaxy may be quiet, or it may be speaking in ways not yet understood. Detection, then, is not a final test but an ongoing process. It refines methods, expands reach, and improves interpretation. Each new telescope, each survey, and each analysis adds to the map of what is known and unknown. The silence remains, but it is measured with increasing precision. In this inward layer, the paradox rests on the edge of perception, where signals must cross distance, survive noise, and match the expectations of observers. The universe may contain many messages or none at all, and current instruments stand between these possibilities, listening within a vast and mostly unexplored field. At the innermost layer of the Fermi Paradox, the question becomes less a search through space, and more a study of what silence can and cannot mean. The silence is real in a narrow scientific sense. No confirmed evidence of extraterrestrial life has been found. No confirmed signal from another technological civilization has been received. No spacecraft, probe, artifact, or atmospheric pattern beyond Earth has been accepted as proof of alien biology or intelligence. Yet this silence is not a single fact with a single explanation. It is an absence measured through incomplete instruments, limited time, uncertain biology, and a universe that hides most of its small worlds behind distance and light. The paradox begins from expectation. Stars are numerous, planets are common, chemistry is widespread. The laws of physics appear consistent across the observable universe. Earth shows that life can arise and intelligence can build instruments. From these facts, it is reasonable to ask why no other example has been found. But the same facts do not guarantee that another example should already be visible. The path from star to signal is long, and each step contains uncertainty. A galaxy rich in planets may still contain few living worlds. A galaxy rich in life may still contain few technological species. A galaxy rich in technological species may still appear quiet if distance, timing, behavior, and detection limits prevent contact. One possible meaning of silence is rarity. Life may be rare because the origin of life is difficult. Complex life may be rare because the transition from microbes to large organisms requires unusual conditions. Intelligence may be rare because evolution does not aim toward technology. Detectable technology may be rare because civilizations may be brief or quiet. Each form of rarity can reduce the chance of detection. None has been proven. The evidence from Earth is too limited to show which step is most difficult. The silence allows rarity as an explanation, but it does not identify the rare step. Another possible meaning is separation. Civilizations, if they exist, may be too far apart in space or too widely separated in time. A signal may take thousands of years to cross part of the Milky Way. A society may rise, change, or fall before another society can hear it. Messages may pass through empty eras when no suitable receivers exist. A galaxy can contain many intelligent species across its history and still show no contact at one moment. Silence then becomes a pattern created by clocks that do not align. It is not emptiness, but non-overlap. A third meaning is quietness by nature or choice. Life does not necessarily produce signals. Microbes do not build transmitters. Complex animals may live without technology. Intelligent beings may communicate in ways that do not leak strongly into space. Technological societies may reduce waste, avoid broad broadcasts, or use narrow beams. They may listen more than they speak. They may not consider interstellar messaging useful. From Earth, motive cannot be measured. A quiet civilization is difficult to distinguish from no civilization at all. Silence may therefore reflect behavior rather than absence. There is also the meaning created by human limitation. The search has covered only a small part of the possible space of signals and signs. It has examined some frequencies, some stars, some times, and some planetary atmospheres. It has not examined the whole galaxy with full sensitivity. It has not watched every star continuously. It has not measured the atmospheres of every rocky planet in a temperate orbit. Instruments improve, but the task remains vast. Silence measured by early surveys is important, but it is not final. The Fermi Paradox is sometimes described as a problem of expectation, but it is also a lesson in scale. The galaxy is large enough for many possibilities to exist beyond immediate evidence. It is also large enough for those possibilities to remain hidden. A civilization may be only a thin layer on one planet. A biosphere may be only a chemical pattern in one atmosphere. A microbial world beneath ice may leave almost no visible trace. A signal may be a narrow beam moving in the wrong direction. The things being sought are small compared with the spaces between stars. Earth itself gives a modest perspective. For most of its history, Earth carries life without technology. For most of its life-bearing time, it gives no radio signal and no artificial light visible across interstellar space. If distant observers had studied Earth long before the present, they might have seen only a living planet through atmospheric clues, and even those clues would vary by era. If they had looked briefly, they might have missed the strongest signs. Earth is not silent from within, but from far away and through most of time it is nearly quiet. This single example warns against assuming that life, even abundant life, must be easy to notice. The paradox also shows the difference between imagination and evidence. Many explanations can be imagined, including rare life, self-destruction, hidden civilizations, difficult travel, unrecognized signals, or simple distance. Some are more scientifically grounded than others, but none should be treated as established without evidence. The careful position is neither certainty of loneliness nor certainty of company. It is uncertainty held within known facts. The known facts are strong enough to motivate the search. They are not strong enough to settle the result. The silence can also be understood as a boundary of knowledge. It marks where current evidence stops. Beyond it, there may be lifeless planets, microbial oceans, complex ecosystems, quiet intelligences, or nothing living at all. Science does not fill that boundary with certainty. It builds better instruments, develops better models, studies Earth's history, explores the solar system, and examines exoplanets more carefully. Each step may reduce the space of uncertainty. A confirmed biosignature would change the question. A confirmed technosignature would change it more. Until then, the paradox remains open, inwardly. The Fermi Paradox is not only about aliens. It is about how one known technological species understands its place in a universe much larger than its evidence. It asks how expectation should be balanced against humility. It shows that numbers alone do not create certainty, and silence alone does not create proof. It brings together cosmology, planetary science, chemistry, evolution, technology, and observation into one slow question. Each field narrows one part of the unknown, while the whole remains unresolved. The deepest meaning of the silence may be its restraint. It does not declare that humanity is alone. It does not declare that the galaxy is crowded. It leaves both possibilities open under the same stars. The universe contains vast structure, many planets, and the materials of life, yet it offers no confirmed second example. That fact is quiet, and it is scientifically honest. It encourages searching without exaggeration and wondering without conclusion. In this final inward region, the Fermi Paradox rests not as an answer, but as a measured absence. It is the calm gap between what exists and what is known, between the many worlds that may be and the single living world that has spoken for itself so far. The question settles into a quieter form. The sky remains wide and the stars remain distant. Galaxies turn slowly in darkness, carrying their old light across space. Around many stars, planets may circle unseen, with rock beneath clouds, ice above oceans, or air shaped by chemistry that has no observer nearby. Some worlds may be lifeless, some may hold simple cells, some may have changed and fallen silent long before their light reaches another shore of space. Science does not yet know which of these paths is common. The Fermi Paradox remains open because the universe gives abundance and distance together. It gives many stars, but not easy access. It gives many planets, but not clear surfaces. It gives chemistry, but not a known probability for life. It gives one example of intelligence on Earth, but no second example for comparison. The silence is therefore not empty certainty. It is a boundary where evidence pauses. In that boundary, the search continues with care. Telescopes gather faint light. Instruments listen across selected frequencies. Planet atmospheres are measured slowly, one difficult signal at a time. Each result adds shape to the unknown, even when it finds no life. The quiet does not become dramatic. It remains steady, patient, and unfinished. Earth moves within this silence as one small living world around one ordinary star. Its oceans, clouds, forests, cities, and signals are brief against cosmic time. Beyond them, space remains vast and mostly unread. The question of other minds stays open beneath the same calm stars, held without conclusion, waiting inside the slow darkness.